In this video, I'm going to show you how to write half reactions for chemical reactions. Now, what a half reaction is exactly how it sounds. It's not exactly half of the entire reaction, but it is, think of it as the important half of a chemical reaction. And this is specifically for chemical reactions that have a change in their oxidation numbers. So you take a chemical reaction like this. This is the simplest one you could pretty much ever be given. You are going to have to do a couple things. The first step is to assign the oxidation states for all the elements involved. So we already know how to assign oxidation states, so you should know it at this point. Fe, when it's alone, it's an element, so it's 0. Oxygen alone in the elemental form is 0. And then here the rules is oxygen is -2. And then if I do my math, that means Fe has to be +3. Okay, so that's first step. Second step is you look for only the elements that change. So since there are only 2 elements in this, it doesn't really matter. I'll show you more complicated ones as we go. What we're going to do is we're going to say, okay, oxygen changed. It went from 0 to -2, and iron changed. It went from 0 to +3. So now what we're going to do is we are going to draw some brackets and connect them. And this is just to highlight the elements that changed. And then we're going to figure out what they did to change. So my second step would normally be to erase everything else, add the electrons, and then balance. There really isn't anything else to erase because this reaction is so simple. We'll do the electron part though. So now let's look at this. Oxygen went from 0 to +3. So how did it do it in terms of electrons? It either gained or lost 3 electrons, and that's what you have to figure out. In this case, this one, iron, lost 3 electrons. And when we lose electrons, this is where the sayings come in. Lose electrons, it's called oxidation, LEO, lose electrons, oxidation. And then oxygen, I don't actually even have to think. Once you identify one of them, for example, iron's the loss, then you have to have a gain somewhere. So the other element has to be the gain. So this one has to be gain electrons, reduction. And in this case, oxygen went from 0 to -2, so it gained 2 electrons. All right, so that's figuring it out. Again, once you know one correctly, then the other one should be easy. It's just the opposite. You can't have electrons lost without electrons gained. So you can't have Leo without Ger. They have to be tied together. So now drawing the half reactions, this is where step 2 comes in. You're going to erase everything but that element. So in other words, if I look at this reaction, iron is what's doing oxidation. So I'm literally going to remove all the oxygens from the reaction. So it's going to look like this. Now notice, I'm also, this Fe2 here that's in the equation, I'm also forgetting about it. We are only going to learn to draw half reactions for a single element. I will show you how to do it for multi-elements, or multiple atoms, but it's not something that you have to know. So here's how it works. That's almost my full half reaction. Now I have to figure out the electrons. So just like when we did our energy unit on thermochemical equations, table I, we remember that if the reaction was exothermic, the energy was added to the right. And in other words, if you're losing energy, it goes on the right side of the arrow or the out. And if you're gaining energy, then you're going to have to add it to the left. Well, the same rules apply for electrons. Nothing's different. So since iron is losing 3 electrons, I'm going to have to add 3 electrons to the right. If it gained those 3 electrons, then I would just add them to the left. So I'd have to put them over here, like the last thing on the left. Just like with energy, being the last thing on the left or the last thing on the right. That's the standard way to do it. Next, it's going to say balance. We can't balance until we get the second reaction done. So the reduction reaction is going to be oxygen. So the way that looks is this way. Oxygen, 0. I'm going to leave space because I'm going to have to add electrons. Turns into oxygen, -2. It's that simple. Now, I'm going to add the electrons. It's going to gain 2 electrons, and since I'm gaining them, I'm going to put them on the left, which is why I left the space there. So I gained 2, I lost 3. And now that's the full half reactions. Last step is to balance with multipliers. So the way we balance is actually pretty simple. All we're going to do is put brackets around them, and we need to make the electrons lost and the electrons gained equal. So we are going to find their first common factor. So in this case, the first common factor is 6. So I'm going to multiply this one by 2 and this one by 3. And now I have balanced half reactions. It is that simple. Now I am going to show you how to do the more advanced version. This is when you do full half reactions. The way it would look is it would look like this. Use a different color. So I use a different color just to hopefully not confuse people. So in these reactions, I'm actually going to keep this here. So there is 2 FEs. So if we look at this, this equation isn't balanced. The way you would balance this equation, the chemical equation, would be by, let's see, putting a 3 here, a 2 here, and then a 4 there. Okay, so it's really 4 iron plus 6 oxygen make 2 Fe2O3. That's the balanced chemical equation. So the way I would do it is I would put it 4 here, and then I would put the balance 2 here. And then the only other thing I would have to do is I'd have to say, okay, with this reaction, 1 iron lost 3, so 4 iron are going to lose 12. So this reaction is taking into account the entire balanced chemical equation. It's a little bit more advanced. You're only going to need to do this. And then I'll do it for this one. So in this one, it's 6 oxygen that are 0. They're going to be gaining 2 each, so 12 electrons, and they're going to turn into 2 of those. So if we look at this, we're done. Gain 12, lost 12. So the benefit of doing the full chemical equations, they're a little bit more complicated, you have more to keep track of, but they're also going to be, when done right, totally balanced and you don't have to worry about it. For the sake of this class, we're only going to have to do the single atom half reactions, and then we balance them. I have 2 more practice problems on the reverse side. We'll go over those now, and then that's it. So this top part, this is a little bit more advanced chemical reaction. We are going to have to assign the oxidation numbers. I'm not going to balance it because I'm not going to show you. It obviously could be balanced. You can see it's not balanced, but I'm not going to show you the more advanced chemical reaction. Maybe I will. So let's take a look. First thing we do is assign the oxidation states. So elements are always 0. It makes life easy. Oxygen, when it happens to be in a compound, is -2. So these are all rules. The only thing I have to really figure out on my own is the Fe and the Al. And in this case, they're both +3. Next step, identify the elements that changed. So if we look, oxygen didn't change. It's -2 on the right side, it's -2 on the left side. So since oxygen didn't change, we do not care about it at all. So I'm only going to be looking at aluminum and iron. All right, so aluminum went from 0 to +3. That means it lost 3 electrons, or -3 E negatives. That's how I write it. So lose electrons is oxidation, which means the other side, I don't even have to think. It's going to be reduction. It has to be. And in this case, it doesn't have to be the same amount. It could be a different number, but it has to be reduction in this case. This one gained 3 electrons. So when we write our half reactions, we're going to remove everything but aluminum for this half reaction and everything but iron for this half reaction. So for the first one, it's going to be Al0, and it lost 3, so, and I'm adding them to the right side of the arrow because it lost 3 electrons. The next one, I'm going to add them to the left side of the arrow because it gained 3 electrons. And then those are my 2 half reactions. In terms of balancing, since the amount of gain and loss is the same, the balancing numbers would be 1, just like in a balanced chemical equation. If everything was balanced, the coefficients would be 1s as well. Now, the more advanced version where you write the whole thing out, for that, we are going to have to balance the chemical equation. So we are going to have to worry, and the balanced chemical equation is going to look like this, a 2 there, and a 2 there, and then that's it. The rest is pretty simple. So it would look like this. 2 Al zeros are going to turn into that, and then here it's going to be I don't need to do the parentheses because they're both ones, but just to separate them out. So that's what the full ones would look like. This last reaction looks weird because based on our rules, you'd say, well, AG's alone, it should be 0, and SN's alone, so it should be 0, and if they're all zeros, and they all should be 1s, and then life should be done. You can see that on a Regents, believe it or not. This question shows up a lot, and that is the most common mistake, is to say balance. They'll say balance this equation, and students will go 1, 1, 1, 1, and they'll get it wrong. Okay. With this equation, here's what's going on. This was a compound. Like, let's say it was AGF, right? F has a rule, it's -1. That makes AG +1. What they're doing is this. They're removing the F and not showing it to you. The same would go here. It would be like SNF2. And then I just used F as an example. It could be anything that was negative. And they're removing it from the equation, and they're just not showing it to you. And the reason they're doing that is because they want to force you to balance this chemical equation by using electrons lost and electrons gained. So what you have to do now is say, okay, these are compounds, so they have to be 0. And then figured out what they did. AG went from 0 or +1 to 0, so that means it gained 1 electron. Gain electrons is reduction, so therefore this one has to be lose electrons, oxidation, and in this case it lost 2 electrons, 0 to +2. Okay, so that's what you have to do in order to balance this. And then you go in and you say, okay, the oxidation half reaction is going to look like this. So SN0 turned into SN +2 electrons. And then the reduction half reaction is going to be AG +1 plus an electron turns into AG0. And then balancing the loss and the gain would be a 1 and a 2, because we can multiply. By multiplying the AG by 2, it gains 2, and then the SN by 1, it stays as losing 2. All right, and then your balancing coefficients will go into the equation, and you would just put a 2 in front of all the AG stuff, and then a 1, or leave that blank in front of the SN stuff, and you're done. All right, so that is how you do these equations. And that should be it. Just be aware anytime you see this type of equation, don't put all 1s. That's automatically wrong. And the reason is a lot of times what can happen, this is a coincidence when it happens more often than not, but balancing the chemical equation can actually get you the proper balancing coefficients for the half reactions. But the problem is that only works some of the time. And so in simpler chemical reactions, it might work more often than not. And so what they're doing is they're trying to prevent you from using standard balancing to get balancing coefficients and forcing you to use oxidation and reduction rules to get balancing coefficients. That's the whole point of this problem. You would never see this anywhere else. It's really just to test your knowledge to see if you know how to do it this way and not an alternative way. And so that concludes the half reaction lesson.